Thank you. I appreciate the invitation by the organizer to allow me to come here and give a summary of the work that we have been working on for the last 4 years. So I'm part of a 6-member team, and we called our model an update to the Peterson et al. Model. And if you are familiar of this field, then you probably recognize half of our team is also the author of the 2011 studies. Okay. We have 3 new members. Kate Thomas, who's a GIS specialist, and she helped us with a lot of data preparation, and also she developed a automated method to construct the main rupture trace. And that really helped us reducing the manual effort to construct the rupture trace. And Chris Milliner, she's worked a lot on using the satellite data and to look at the fault displacement hazard. And I think he's a postdoc at Caltech now, right? So, and I was invited to join the team, and the reason is that both Rui and Mark think that I have some experience in the ground motion modeling, and they thought that they can transfer that knowledge into the modeling of fault displacement. That's what I thought too 4 years ago, but then after we get the data and dig deeper into the data set, then I realized it's not as easy as developing ground motion models. And so we ended up trying different things, and took us 3 years to complete the project. And so that's something I really appreciate the opportunity, because it forces me to go outside my comfort zone, which is normal distribution. And I have to look at other type of distribution. And I was overwhelmed with the literatures and trying to learn them on the fly. And fortunately, we just accidentally run into one distribution that really worked well with the displacement data. And therefore, we can write a report after 3 years of study. Co-seismic surface displacement poses a geologic hazard and to structures and lifeline that cross active faults. And we typically use the probabilistic methods to assess the potential amount of fault displacement in the future earthquakes. And one of the main input of that hazard analysis is the fault displacement model. That is a model that describes the probability distribution of surface principal displacement. Okay, remember, it's principal displacement. It doesn't involve distributed displacement. And it's the probability at a point along rupture. Okay, so we updated the model of Peterson et al. Because Peterson et al., not only because they invited me to join their team, but because the Peterson et al. Study is one of the key model that has been used in the practice so far. Okay, so there's a question of why do we bother to update the Peterson et al. Model? And of course, one of the main reasons is that we now have a better data set. The data set is compiled by the Fault Displacement Hazard Initiative project, and it's not only compiled, but the database developers spent a lot of time to vet the data. So it's a very, not only comprehensive, but also vetted. And the data set includes 3 types of earthquakes. Strike slip is one of them, the reverse and normal as well. And we decided to start with the strike slip earthquake, and we go through the data set, and we selected 29 strike slip earthquakes, from which we have gathered about 3,000 displacement data points. And so here is, I'm trying to show you one of the main predictors of displacement, that is the position of a measurement along the main rupture trace. We call the little L, and the big L is the length of the rupture trace. For fault displacement hazard, we don't use little L directly. Instead, we use the normalize. It's normalized to the length of the rupture trace. So that way, it allows us to combine, to pull data from different sides of earthquakes so that we can use the pool data to give us a better or more data constraint on the shape of the along strike variation of the slip. And we also used something called L2LF. That is L2L, but folded at the midpoint of rupture. So this is done because we typically, or in Peterson et al., we assume that the mean or the median displacement distribution is symmetric to the midpoint of the ruptures. Okay, so this slide shows both the old data set that's used in the Peterson et al., that is in magenta color, and the new data set that coming out of the FDHI database, that's in the blue color. And you can see that this is a bigger data set. There are quite a bit of overlap of earthquake between the two data sets, but I think this overall, the new data set is more complete, has more earthquakes, and it covers more larger magnitude earthquakes. Okay, this slide shows the profile of the displacement for each individual earthquake. So you can see that some of the earthquakes, such as the Lander earthquake, is very well measured. There's a lot of like 300, maybe 400 data points from the Lander earthquakes. And also the displacement measurement from the Lander earthquake is a lot more complicated. It shows a much complex pattern along strike. And in contrast, that's the Denali earthquakes. It's much longer in length than the Lander. It has relatively fewer data points than Landers, but one thing that quite visually very visual contrast between these two is that the Denali earthquake, along strike variation seems to be a lot simpler than what we see in Lander. In Lander, we see slip valleys, and that's not seen in Denali earthquakes. So let's just, since this is an update to Peterson et al., so I just cut to the chase and list four major changes to the Peterson et al. Models. So the first one is about the probability distribution of the principal surface displacement. In Peterson et al., they use a Gaussian distribution. We change it so that to something we call the negative exponentially modified Gaussian. So I want to emphasize this is modified Gaussian because it's really a Gaussian distribution with a Gaussian variate minus an exponential variate. Okay. So the minus is the negative. The exponentially means the scepter hand of exponential variate. Okay. And Peterson et al. Use a linear magnitude scaling for the mean parameters, and we use bilinear. Okay. And this is supported by the data. I'll show you later a slide that sort of support the use of a bilinear magnitude scaling. And by the way, the bilinear magnitude scaling is also used in ground motion models. So this is not. We're sort of a lot of the things. Well, because of my background mostly in ground motion models, so it's very natural for us, for me, to borrow something from the ground motion model. So, and another changes is that the Peterson et al. Use a fixed effect model only, and in ground motion model, we know that there is a random earthquake effect on the mean as well. So we added this random effects into our model, and it has and we find that the variance of the earthquake, the random earthquake effect, is actually magnitude dependent. Okay. Again, I mean, this magnitude dependence we also see in the ground motion model. Okay. The last thing is about the within earthquake variance. In Peterson et al., that variance is a constant, where in our updated model, the variance is decreasing toward the midpoint of the rupture trace. Okay, so about the probability distribution. So depending on the quantity that we use, that we treat as the response variable, people use different type of distribution. For example, in Yang et al., when they model the normal faulting displacement data, they model the displacement as the product of a normalized displacement times the normalization factor being the average displacement, and times the average displacement itself again. So in this way, the normalized displacement is assumed to be a y-o or gamma distribution, and the average displacement is a log normal distribution. So we can do the same thing normalizing with respect to the maximum displacement, but because it's normalizing to the maximum, the normalized displacement is a beta distribution that has a support between 0 and 1. So the same thing was similar thing was done in Moss and Ross study for the reverse earthquake. Okay, but in Peterson et al., instead of using D as the response variable, they use the log D as the response variable. And they assume that log D is distributed as a normal distribution. And I will show you later that, that this assumption doesn't fit the data really well. So we have to make some changes. So here is a plot of residuals versus position along strike. And what we did is we just refit Peterson et al. Nothing was changed. We only swap out the data set from their old data set to the new FDHI data set. So it's still a normality assumptions, and the residual is the, observed minus predicted mean. Okay, so you can see that this is not. There are more residuals at the negative side than the normal distribution would suggest. So if we here is we plot the residual here in histograms, and you can clearly see that the residual distribution is not symmetric, and it has a fatter tail on the left and a thinner tail on the right. Okay, and the red curve here is fitting the residual with a normal distribution. You can clearly see that the normal distribution doesn't fit the residual histogram very well. And the black curve is fitting the residuals to the negative exponentially modified Gaussian, or we call it NEMG, and it fits the residual really, really well. So that gives us the justification for switching from normal to NEMG. So when we recognize that the residual doesn't distribute it symmetrically, and it has it's actually left skewed, so we went out and tried to find distribution that's still related to Gaussian distribution, but it's a form of modification. What we're looking for is a way to introduce skewness into normal. Okay, and there's a lot of literature about how to do that, and one of the distribution is called skew normal. It includes a third parameter in addition to the mean and standard deviation. It includes a third parameters that regulate the skewness of a distribution. Okay, and we tried that, and we also tried the skew T distribution. Both of them work relatively well, but we decided that they are very cumbersome to use. And we don't know if the practitioner will be receptive to this kind of relatively complex distribution. So we set out to find another way to modify the Gaussian distribution, maybe just starting from the Gaussian distribution and subtract from the Gaussian another random variable that will force the Gaussian into a skew shape. So by accident, we run into the exponentially modified Gaussian, but that distribution is right skewed, so we have to change the sign here. Instead of plus E, we use the negative E, so we'll force the distribution to become left skewed. Okay, so in this NEMG distribution, there are two components. One is the G component, that's a normal variate. And E is an exponential variate. Okay, so we like that stochastic representation because we can now treat the E as reflecting the effects of interior tapering on the displacement. And so it has been well known that the interior taper occurred near the edge of two adjacent ruptures. Okay, and let me show you one example. This is a slip profile from the 1989 Superstition Hill earthquakes. And Cohen et al. Went in and looked at the data, and they use automated method to segment the ruptures. And this is what they come out with. This is one segment, the other, the second segment, and the third segment. You can see that between segment, what they call segment 0 and segment 1, the slip from segment 2 is actually decaying. That's sort of like, that's the tapering effect that I'm talking about. And also the same thing at the at the interacting or the overlapping section, the segment 1's slip displacement also was tapered. Okay, the same thing can be said about between the segment 0 and segment 1. Okay, so there is widespread interior tapering effects, but the effect is sporadic. Displacement away from the interacting edge are not tapered. Okay. You can see that you can still model the displacement here with a traditional slip model or a shape profile. So it's only where they're near the boundary of this two segment that we can see the tapering of the displacement. So so the tapering effect on displacement can be modeled, and it can be modeled explicitly, such as was done by Norm and his and Nick. They decompose a rupture into segments, and they model the slip within the individual segments. And in that case, the interior taper becomes the edge taper. Okay. We choose to model it probabilistically. We acknowledge the presence of the segmentation, but we do not attempt to identify them in each earthquake, because to us that seems to be a difficult and sometimes ambiguous task. The automated methods sometimes require operator intervention. And so what we did is that we used the E component to capture the tapering effects. That's, we assume the E component, or the new parameter of the E component, is a constant. So what we actually model is the compound distribution of the taper effects. That include randomness in the occurrence, the location of the taper, and the taper width, and the depth of the taper. Okay. So we lump all the randomness into a single random variable. Okay. So to recap, again, this is the residuals from the simple update to the Peterson et al. In Peterson et al., the log D is modeled as a Gaussian variate. In our new model, we add this, we subtract exponential. And so this new distribution now has three parameters: the mu, the sigma, that's the mean of the Gaussian. Sigma is the standard deviation of the Gaussian. And the E is exponential with a rate of 1 over nu. And it represents the compound effects of the interior taper. So with this term, it will effectively pick up all the low value or the negative residual in this domain, and that couldn't be modeled by just simply a Gaussian distribution. So one thing about the NEMG distribution is that it's always left skewed. And another benefit of that is that the deployment is straightforward and numerically efficient. So there is an analytic expression for the CDF and PDF or the NEMG, and in that expression, only the standard normal distribution function needs to be used. So this is something that can easily be implemented in Fortran, even in Excel. And if you have other scientific engineering computational platforms such as MATLAB, there are built-in functions to do the calculation. Okay, so I'll probably skip this one. So, and the second change to the Peterson et al. Is that we go from the linear magnitude scaling for the new parameters, for the mu parameters, to a bilinear scaling. Okay, so this is this plot showing the random R-square term as a function of magnitudes. So you can see that the rate of increase with magnitude changes. It's steeper for magnitude less than 7, and then when we go beyond 7, the rate becomes flatter. Okay. And to model this, we need 3 parameters. That is the hinge point of the transition from the steeper rate to the slower rate. And the other 2 parameters is the rate at smaller magnitude and rate at a larger magnitudes. Okay, so random effects on the mu parameters. So random effects is a standard feature of ground motion model. If not properly treated, a few well-measured earthquake may bias the estimation of magnitude scaling. I mean, this is something that's well known in ground motion model development. Okay. The last improvement is that the variance in the Peterson et al. Model is a constant. Based on the empirical analysis of the data, we find that the sigma actually varies with L to L, with the position that's the position or the normalized position along the strike. And the sigma is higher near at the small L to LF, that is near the fault edge, and then it starts to decreases toward the center. Okay, so putting all 4 changes that I just described, this is the functional form of our models. Okay, so we do the regression and we got our estimates of the model coefficients, and then we look at the residual to see if our fitted model is a good fit to the displacement data. And this shows the within earthquake residuals versus plotted versus position, plotted versus magnitude. And this is showing the histogram of the residuals. And this is the CDF. And this is the QQ plot. And in each of this plot, we're plotting the also the fitted normal distribution. And we can see that it's a pretty good fit to data. Okay, well. Right. So let me show you some comparison. And this is for a magnitude 7.9 earthquake. And you can see that for the median, that's here, the two models are not as different as we see in the 95th percentile. I think one thing to note is that at the 95th percentile, the new model actually predict a lower number, a much lower number than what Peterson et al. Predict. Okay, so this is again the same thing, but plotting the predicted percentile as a function of magnitude at 3 different locations. And you can see the difference. The Peterson et al. Has a linear magnitude scaling, and our model has a bilinear magnitude scaling. Okay, now the comparison in the hazard domain. The green curve is, okay, this is, hazard calculation is for a magnitude 8.3 scenarios. It has a return period of 2,500 years. And if we use the Peterson et al.'s model, that gives us the hazard curve showing us the green line. And if we implement all the changes that we discussed earlier, except for the distribution assumption, we get the blue line. Okay, so the difference between these two represent 3 of the changes we make. Okay, now the red line is actually the hazard curve using our new models. So going from here to here, we can see that just by adopting a new distribution, type of distribution, we also see a drop in the hazard curve. So that gives you a sense of how each individual, well, how the assumption about the distribution impact the hazard and how the other 3 impact hazard. It gives you a sense of the relative importance. Okay, now the model application range, the data range is, the data we use in our model development is from 6 to 7.9, but we feel that we can actually extend the upper bound from 7.9 to 8.3, and this is because we look at how our magnitude scaling relation predict the average displacement data that's collected in 3 other studies, in the Wells and Coppersmith in 1994, and Wells and Young's, that's the updated data set of the Wells and Coppersmith, and also data collected by Anderson et al. 2021. What's unique about these 3 data sets compared to the FDHI data set is that they include several earthquakes that has a magnitude that's larger than 7.9. So it will, if our magnitude scaling relationship can fit those average displacement data in terms of magnitude scaling, I think that's an outcome that will support us to extend our applicable range from 7.9 to 8.3. As you can see that it actually, our model actually captured the displacement data at magnitude larger than 7.9 pretty well. So that's the base. Because of this, we decided that we can extend our applicable range from 7.9 to 8.3. So in conclusion, in addition to a beta and a larger data set, we have implemented 4 important changes to the formulation of Peterson et al. And these changes result in a better, in the sense of distributional fit to the displacement data. And they also result in more reasonable prediction of upper percentile, say the 95th percentile. So that's the work for phase 1. In phase 2, we still have a lot of work to do, and in phase 2, we will address a correlation issues that has been implemented like in norms model. I think those correlation will be useful, and we need to address that, and we haven't addressed it yet. So, and also our current model is for reverse and normal ruptures, and we have planned to develop the model using the same methodology and apply it to reverse and normal data and develop separate model for these two type of earthquakes. And we also have planned to develop a model for secondary or distributed displacement. Okay, so it's, you know, a lot of work needs to be done. So that will keep me busy for a while. So thank you.